Well, I thought I would take a video here and do a frequency analysis of this 46-year-old CB radio. It's an old Midland 13-893 23 channel sideband transceiver. It was made in around May of 1975, so that's a pretty old transceiver. But we're going to do a frequency stability analysis using an HP 5371A frequency and time interval analyzer. So I'll get everything set up and we'll continue the video. Alrighty, got this thing all set up. We are going to take the tap off, test point 5, which is the output of the mixer that combines this crystal oscillator here and this crystal oscillator, and the output is here, comes down to test point 5, which should be around 19 some odd megahertz. These old radios use a crystal synthesis method of mixing two different crystals together to determine or to generate the frequency of interest. So we're going to take the test point here so that we get all of the errors and drifting from both these crystals, and we'll see what happens. And we're going to be, standard measurement is going to be, well, we'll start with 10 samples first, 10 measurements, one block, and then we'll bump it up to 100. So let me get these things going here and we'll see what happens. Alrighty, here's the first bit of data here. We got about a 19.354 megahertz signal. We have our mean frequency, and we have a standard deviation of 734 millihertz, which is quite a bit for something like this. But now I'm going to change the settings, and we're going to do some graphs and show drift over time. Alright, now we're going to change the measurement parameters here. So we're going to go to function. We're going to change the number of measurements to 100. Then we're going to go to the graphic mode, and we're going to select time graph. And this function here we will set it up for single. We'll restart it, and in about a minute and a half I'll come back and show you the graph. Alrighty, here's our graph. We ran this sample for 100 samples. Took about 1.6 minutes to obtain this graph. And now we can go in and do some more detailed looks at how far this radio has drifted over a minute and a half. This radio is turned on cold. So it started here originally at around 19.35 megahertz and has drifted upwards considerably. Now we can use the cursor here and we can find out just how far it's drifted. So at sample 40, it drifted up 2.754 hertz and made a large jump, and then kind of leveled off, and it just gradually goes up and up and up and up. And over 1.6 minutes, it has drifted just a little over 6.5 hertz, which is typical for old crystal radios, crystal controlled rigs that are this old. Once it's been on for a while, it will settle down and jump up and down and up and down and up and down. But having an instrument like this is really handy for doing this sort of thing. You can also do Allan deviation plots with this instrument, and those are pretty interesting to do. I currently use a computer to do these plots, so I will probably show that too. But just the instrument itself, you can do some pretty interesting plots. And we can go back to numeric, and this happens to be displayed out to many decimal places. The average standard deviation was a little over 2 hertz, And this is, you know, it's awesome what this thing will do, especially when you give it enough a large sample size. It's really astonishing. But let me get something else set up and we'll go from there. All right, now we're at the in a different mode here, looking at the statistics display. This will give us the mean frequency, standard deviation, maximum and minimum frequency, the RMS frequency, and we get Allan variations and so forth. And so far the radio is starting to settle down and getting a little bit better. But we can also go to just the results, and you can see all 10 measurements once they show up. And they're all pretty close. They're all just a few hundred millihertz off, which is pretty good for a crystal radio. And we can also view the results and statistics on one page. Should take about 10 seconds here. And there we go. So we got a standard deviation that's now down to 49 millihertz. And we can go back to statistics. We can go to bold. And this will make some nice bold fonts here, so it's a little easier to read. And you just get the normalized frequency, the mean frequency, and the standard deviation. So let me do one more thing here, and we'll be right back. All right, here's the next next graph. You see the radio kind of settled down a little bit. It was jumping around a few hundred millihertz. And then right about here, right about 46 seconds into the capture, it starts dropping by quite a bit. By about a hertz or so. I guess that's not too bad for an old junker like that, but it's real interesting to be able to do this kind of stuff, because you can watch this out on your frequency counter, but it's really difficult to plot this stuff without software or an instrument like this. So it really gives you an idea of just how nothing is on frequency, and it's something else. I've tried this on other sources like the high-end HP 10811 ovenized reference oscillators do have a little bit, only a couple of millihertz or so, maybe 10 millihertz. And I even tested a GPS disciplined oscillator, and it even had less drift. But something like this is certainly noticeable and makes for a good demonstration. So anyhow, let me decide if I want to move on to something else here, and we'll maybe do I'll do a Allan deviation plot. All right, I'm getting ready to do an Allan deviation plot, and for this I like to use some software called Timelab. It's free. You can download it off the internet. You can also download another set of GPIB tools that comes with a plotter, emulator, spectrum analyzer, phase noise, which is nice to do. So maybe I'll do that in another video. But what I'll start here is I'll start a time plot, Allan deviation plot, excuse me, and I'll run it for 1,000 seconds, and we'll see what she looks like then. But what we could do is go in here to acquire. We go down to my 5371A, select that. I'll put a note in here of let's say Midland CB radio. And we're going to do it in the frequency domain, and we're just going to put 19 megahertz. E to the 7. And we're going to run it for 1,000 seconds. So we'll start the measurement and see what happens. Well, I would consider that actually a fairly decent Allan deviation plot for a 46-year-old radio. It only deviated about 300 millihertz during this whole time this plot was being graphed on the screen here. So yeah, that's pretty cool for this ancient old thing. It held frequency pretty well. It was only varying about 300 millihertz up and down, or thereabouts, maybe 400. But it was doing that now. Oh, it's almost 500 millihertz. I would consider that pretty good for a radio as old as this. So I'm going to try one more thing. I'm going to do a phase noise test, and I'm going to use my HP70K series spectrum analyzer, and we'll run all this through the attenuator and make sure that we don't blow nothing up. Anyway, we'll be back. Well, even the phase noise is pretty good for a 46-year-old radio. Looks like the phase noise level at 10 kilohertz is almost 100 dB, 99.8 dB down. Something else. And this thing is actually a pretty decent little radio. I mean, wow. Anyway, I think this is about it for all, or about all for now. So, if you like this video, hey, just let me know. If you thought it was stupid, well, yeah, say that too. So, anyway, have a good one.